Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Welcome to Madam Hida channel. For this lesson, we will continue on chapter 1, Molecules of Life. In the previous lesson, you have learned about subtopic 1.1, water. For this lesson, we will be focusing on subtopic 1.2, carbohydrates. Carbohydrates act as the main substrate in cellular respiration such as glucose. It also acts as energy sources and food storage in animal in the form of glycogen and also starch in plant. Carbohydrates also act as building block in cellular components such as cellulose in the plant cell wall. Carbohydrate can be classified into three different classes, namely as monosaccharides, disaccharides, and polysaccharides. Monosaccharide is the simplest sugar. It can divide the sugar based on the number of carbon atoms or based on the location of carbonyl group. Monosaccharide with 3 carbon known as triose, 5 carbon known as pentose, and 6 carbon known as hexose. Whereas, based on the location of carbonyl group, C double bond O. The carbonyl group can be positioned in anywhere in the carbon skeleton. If the carbonyl group located at the end of the carbon skeleton, then the sugar is known as aldose. If the carbonyl group is located in the middle of the carbon skeleton, then the sugar known as ketose. Disaccharide is composed of 2 monosaccharides and joined by glycosidic linkage through condensation process. Disaccharide also can be broken down back to monosaccharides through hydrolysis process. There are 3 examples of disaccharide. The first is maltose, second is sucrose, the third is lactose. The third class of carbohydrate is polysaccharides. Polysaccharide is made up of many monosaccharides and also joined by glycosidic linkage through condensation process. It also can be hydrolyzed back into monosaccharides through hydrolysis process. The 3 examples of polysaccharides are starch, glycogen, and cellulose. Monosaccharide can be classified based on the number of carbon atoms in the carbon skeleton. If the carbon skeleton consists of 3 carbon, then the sugar known as triose sugar. The example of triose sugar is glyceraldehyde or dihydroxyacetone. And pentose sugar is when the number of carbon atoms in the carbon skeleton is 5, such as ribose, ribulose, or deoxyribose. And if the number of carbon atoms is 6, then it's known as hexose sugar, such as glucose, galactose, and fructose. How to number the carbon atom within the carbon skeleton? The carbonyl group must be numbered as the lowest carbon number. Number 1, 2, 3. Next, look at glucose. Carbon 1, 2, 3, 4, 5, and 6. Monosaccharide can be divided into different sugar based on the location of carbonyl group. There are 2 different sugars known as aldose or ketose sugar. when the carbonyl group is located at the end of the carbon skeleton, then the sugar is known as aldose. From this figure, we can label the carbon number according to the position of the carbonyl group. 1, 2, 3, 4, 5, 6. So the position of carbonyl group is located at the end of the carbon skeleton at carbon number 1. Whereas for the ketose sugar, the carbonyl group is located at any position within the carbon skeleton. From this figure in the fructose molecule, we can label the carbon number based on the position of carbonyl group. This is carbon number 1, number 2, number 3, number 4, number 5, and number 6. So the carbonyl group is located at carbon number 2. So the example of aldose sugar is glyceraldehyde, ribose, glucose, and galactose. And the example of ketose sugar are dihydroxyacetone, ribulose, and fructose. And class, from this diagram between glucose and galactose, if I can draw the line which represents the mirror here, focus on carbon number 4. Glucose and galactose, also known as enantiomer, or we call it stereoisomer, which means galactose become the mirror image of glucose, or glucose become the mirror image of galactose, but only for carbon number 4. Linear and ring structures of hexose. Hexose sugar, which have 6 carbon within the carbon skeleton, such as glucose, galactose, and fructose. In the aqueous condition, the ring forms are favored compared to the linear form due to its ability, which means in the aqueous condition, the linear form will convert into the ring form to become more stable. The main monosaccharide in human body is glucose, and glucose can exist in 2 different forms which known as isomer. Do you know what is isomer? Isomer is when the molecule have the same molecular formula but with different molecular structure. In this case, this is the linear form of glucose with the molecular formula with CN, H2N, ON, or C6, H12O6. But glucose can exist in 2 different ring forms, alpha glucose or beta glucose. These 2 structures differ based on the position of OH at carbon number 1. If the OH position itself below the plane, then it is known as alpha glucose. Whereas when the OH position itself above the plane, then it is called as beta glucose. So let's see how to draw the alpha glucose and beta glucose in the ring structure. First, you have to draw the hexagon. Then you have to draw the bond and fill the hydroxyl, hydrogen or carbon atom. Make sure the bond is directly point to the specific atom. So from here, we can label the carbon number. Here is carbon number 1, number 2, number 3, 4, 5, and 6. So this molecule known as alpha glucose. Do you know why? Yes, exactly. Because OH projects below the plane. What about the beta glucose structure? Let's try it. Again, you have to draw the hexagon. Then you have to show the bond. And again, complete with hydrogen, oxygen or carbon. Next, let's number the carbon. Here is number 1, number 2, number 3, number 4, 5, and 6. So, look at the position of hydroxyl group at carbon number 1. Yes, it is positioned at the above the plane. So, this structure known as beta glucose. As I have mentioned earlier, carbohydrate can be classified into 3 different classes, and the second class is disaccharides. Disaccharide composed of 2 monosaccharides by condensation process. And there are 3 examples of disaccharides, namely as maltose, which mainly is malt sugar. We have sucrose, such as cane sugar, and lactose is milk sugar. And here, we can see that maltose is made up from alpha-glucose monomer plus alpha-glucose monomer. And sucrose from alpha-glucose and beta-fructose, while lactose is combination of beta-galactose and beta-glucose. So, after this, we will be focusing on maltose. Maltose can be found in grains known as malt sugar, and it is formed from the condensation process between 2 molecules of alpha glucose. So this is the structure of maltose, which link between the 2 monomers by alpha 1,4 glycosidic linkage. Do you know why it is known as alpha? Because the monomers used are alpha glucose. And do you know why is there 1 or 4? 1 and 4 is because the link between the 2 monomers is involve carbon number 1 and carbon number 4. And what is meant by glycosidic linkage? Carbohydrate involve glycosidic linkage. So, monosaccharide combined with another monosaccharide will form disaccharide through condensation process. In condensation process, it involves the removal of water molecule. And when we broken down the disaccharide into monosaccharides, it will undergo hydrolysis process by the addition of water molecule. This diagram shows how the condensation reaction takes place in the synthesis or formation of maltose. When one monomer alpha glucose combines with another monomer alpha glucose, one water molecule will be removed from carbon number 1 of the first alpha glucose and from carbon number 4 of the second alpha glucose. The process known as condensation, which involves the removal of water molecule, and the product known as maltose. The bond that link between the two monomers known as alpha 1,4 glycosidic linkage. This diagram shows the hydrolysis reaction which takes place in the process of breaking down maltose into monosaccharides alpha glucose. This structure shows the structure of maltose that join together by alpha 1,4 glycosidic linkage between the two monomers. It shows the addition of water molecule into the glycosidic linkage. Through the hydrolysis process, it will divide it into two monosaccharide alpha glucose. This figure shows how the condensation and hydrolysis reaction takes place in the synthesis and breakdown of maltose. We start with the two alpha glucose monomers, show the removal of water molecule from the two monomers, and shows the two arrows which represents condensation and hydrolysis. Then we draw the structure of maltose, name the bond that link the two monomers as alpha 1,4 glycosidic linkage, and show the addition of water molecules into the linkage bond. Polysaccharide consists of many monosaccharides and linked by glycosidic linkage through condensation process. And all polysaccharides are large molecule and all are insoluble in water, which means they are not affect the water potential except for glycogen. and all polysaccharides are easily hydrolyzed except for cellulose. So, let's look at the first polysaccharide, which is starch. Starch exists in two forms. First, as amylose, and second is amylopectin. What are the differences between those two, amylose and amylopectin? Both amylose and amylopectin compose of the same subunit, which is alpha glucose. But the difference is amylose is a simple and unbranched helical chain, whereas amylopectin is a complex and has branch. Glycogen is the major storage carbohydrate in animal cells and also in fungi. The structure of glycogen is made up of short and highly branched of alpha glucose. So the monomer of glycogen is alpha glucose. And the structure of glycogen is similar to amylopectin, but it is more extensively branched and more water soluble compared to amylopectin, as the starch or amylopectin is insoluble in water. Cellulose is the structural component of plant cell wall and make the cell wall very stable. The monomers for cellulose is beta-glucose. The structure of cellulose is long and unbranched chains. The bond between monomers in cellulose is beta-1,4 glycosidic linkage due to the monomers used are beta-glucose. Since the cellulose is unbranched chain, but the cellulose can be arranged in a parallel form that are held together by hydrogen bonds to ensure that it is strong enough to make up or to protect the plant cell. Every beta-glucose monomer is upside down with respect to its neighboring. This is the first beta-glucose monomer with the normal structure. This is the second beta-glucose monomer with the upside down structure. And the third monomer is the original structure. The fourth is the upside down structure. Do you know why cellulose material is suitable for plant cell wall? It is due to the hard, strong and rigid structure of the cellulose due to the hydrogen bond that link between the adjacent chain of cellulose. So, it suits to give support or mechanical strength and give shape to the plant cell. So that's all from Madam Hida. Till we meet again in the next lesson. See you! So that's all from Madam Hida. Thanks for watching.